In this chapter, we're going to be looking at chapter 2, sections 1, 2, and 3. We're going to kind of get an early introduction into some of the early ideas of matter, as well as those ideas and theories that still hold today. We're going to look at what makes up an atom. We'll kind of see early on that some of the early theories of atoms basically said that these were indivisible particles, that you couldn't go any smaller than an atom. But there's been further experimentation that shows that, in fact, atoms are made up of what we call subatomic particles. And we'll see we'll look at the experiments that were used to show this. And then we'll round out this section by looking at how we use symbols and how we calculate the average atomic mass of an element. So that's where we're going to be going. So let's start off by looking at some of the early theories of what an atom is, or what makes up stuff. The concept of atoms was first proposed by the Greek philosophers Leucippus and Democritus, and this was way back when, 5th century BC. They kind of got it sort of right, where they basically said everything was made up of indivisible particles. Um, you could cut something in half and cut it in half and cut it in half and cut it in half until you get down to a single atom, and that atom can't be divided anymore. And in fact, the Greek or the word atom comes from the Greek atomos, which means indivisible. A little later, Aristotle and others believed that matter consisted of various combinations of the four elements, quote unquote, or fire, earth, air, and water. And it kind of stayed like that for a couple millennia. It wasn't until about 2,000 years later that the English school teacher John Dalton proposed his atomic theory. And this is pretty much what we still hold to today. Um, Dalton's atomic theory comes in five precepts. Number one, matter is composed of exceedingly small particles called atoms. And an atom is the smallest unit of an element that can participate in a chemical change. And number two, an element consists of only one type of atom, which has a mass that is characteristic of that element and is the same for all atoms of that element. So this kind of seems like, yeah, duh, but like it's so foundational to chemistry because it's basically saying, for example, if you have a copper penny, and like a real copper penny made out of complete copper, not one that's just, a more recent one that's like copper coated. But if you have a penny that's made out of pure copper, every single atom of that penny is made up of copper. And every single atom has exactly the same traits, has exactly the same properties, and they all have the exact same mass. Now, in contrast to that, the third precept is that atoms of one element differ in properties from atoms of all other elements. So copper will have different properties than, say, carbon, or magnesium will have different properties than silicon. So atoms of one element differ in properties from those of another. A compound consists of atoms of two or more elements combined in a small whole number ratio. In a given compound, the number of atoms of each of its elements are always present in the same ratio. What this is basically saying, for example, water. Water, there will always be hydrogen and oxygen present in a 2-to-1 ratio. If it's another ratio, it's not water anymore. For example, if there's an extra hydrogen there, this is a compound known as hydronium, or an ion known as hydronium. That is not the same as water. So a compound consists of atoms with two or more elements, and they're always combined in a small whole number ratio. So it's never, you won't have like half an atom combining with the whole another element. So this little diagram or a picture on the right, that black solid at the bottom of that cup is something known as copper oxide. And it's a ratio of one copper atom to one oxygen atom. And that form of copper oxide will always have one a ratio of one copper to one oxygen atom. That this form will never have any different ratio. Now, copper might combine with oxygen in a different ratio, and in that case, that's a different compound. And then finally, atoms are neither created nor destroyed during a chemical change, but are instead rearranged to yield substances that are different from those present before the change. So again, I'm going to use copper and oxygen as an example. So here's copper down here, copper metal. Here's oxygen floating up in the air. And when copper and oxygen combine, they will make this compound copper oxide. Now, the amount of atoms does not change. All that happens is there's a change in the composition or the way the atoms are bonded together. So let's do a quick problem to test our knowledge of Dalton's theory. Um, and so here we have kind of a very generic example of a chemical reaction. So we have two of these green atoms, whatever they are, and they're going to react with two of these blue atoms. Now, if we look at the products afterwards, notice what happens. There's one blue atom and one green atom. Now, there's a rearrangement, and that's fine. That's what happens in a chemical reaction. But does this support Dalton's theory, or is this not like a correct reaction? And so if you take a look at it, even though atoms have arranged, this does violate Dalton's theory, specifically the last one that we just talked about, because there are a different number of atoms on the left side of the reaction than the right. So how would we fix something like this? Well, if we start with two greens and two blues, then we need to end. So maybe there will be another compound or molecule of this compound that has a green atom bonded to a blue one. And that would be the best way to fix it. So that it obeys that fifth concept of Dalton's atomic theory. So atoms can be bonded to other things. We just cannot add or take away atoms in the chemical reaction. Now, in relation to this, there was a French chemist named Joseph Proust that his work kind of also informed Dalton, and I'll show you how on the next page. But Joseph Proust, his work led to something known as the law of definite proportions or law of constant composition. And this basically says that all samples of a pure compound contain the same elements in the same proportion by mass. Now, what does that mean? Let's say we have a couple bottles of the same exact substance. So I'm just going to call this substance A. And A is made up of carbon and hydrogen. And this A over here is made up of carbon and hydrogen. Now, if I were to take a 1 gram sample out of this bottle on the left and take a 10 gram sample out of the bottle on the right, because they're the same substance, if I were to analyze how many carbon atoms there are, or what's the mass of carbon to hydrogen over here, the ratio of carbon to hydrogen for A would be the exact same ratio of carbon to hydrogen for the bottle on the right. As long as they are, we know that they are the same substance. So this table here kind of emphasizes that. Here, this scientist took 3 samples of this compound called isooctane. You don't need to know what that is. As a little side note, isooctane is one of those compounds that's found in gasoline, and it actually contributes to that octane rating that you see, like 87 or 89 or 91, whatever is there on the gas pump. You don't need to know that, but just a little fun fact for the day. Um, but whoever got these readings, they took 3 separate samples of isooctane, maybe from 3 different bottles. He, found 3 bottles of isooctane and took a sample from each of them. And in each case, analyzed how much carbon there is and how much hydrogen there is. Now you'll notice the total masses for each of these 3 samples is different. So how much sample he took out of the bottle is different. But when you look at the ratio of carbon to hydrogen for A, so take 14.82, divided it by 2.78 to get a ratio, it basically said, well, for every gram of hydrogen, there's 5.33 grams of carbon. And then he found the same thing for sample B. That ratio is the same. And then the same thing for sample C. That ratio is the same. So this experiment helps demonstrate that law of definite proportions. All samples of a pure compound contain the same elements in the same proportion by mass. Now, one important thing to note is that the reverse of that statement is not necessarily true. Always true, I should say, is not always true. Meaning that samples that have the same mass ratio are not necessarily the same substance. There are many other compounds that have that ratio of 5.33 grams of carbon to 1 gram of hydrogen, and they aren't identified as isooctane. So you have to know first that you're taking samples of the same compound for this law to be true. If you don't know that for a fact, then you can't say that just because they have the same mass ratio, that they're actually equivalent or that they're the same compound. Now, if we go back to James Dalton, sorry, John Dalton, um, he kind of took Proust's work and ran with it and used some of his own experiments to formulate the law of multiple proportions, which says that when 2 elements react to form more than one compound, a fixed mass of one element will react with masses of the other element in a ratio of small whole numbers. Now it's kind of a mouthful, and there's a lot of confusing things here. So the best way to demonstrate this law is to kind of see it in action. So for example, When copper reacts with chlorine, it can potentially make two different compounds. One of those compounds is a green solid. So here's one form of copper and copper chloride, and another is brown. And I just realized I don't have a brown color in here, so I'm gonna use this. So pretend that's brown. Now we know these are two different compounds because they have two different colors. So copper and chlorine, when they react, it will form either the green compound or the brown one. Here's the interesting thing. When we analyze the composition of the green compound, we see that the ratio of copper to chlorine is 1 gram of copper for every 0.558 grams of chlorine. And the ratio in the brown compound, the ratio of copper to chlorine is for 1 gram of copper, there's 1.116 grams of chlorine. So that alone kind of tells you these are different compounds. Now, that's pretty much all we can get if that's all that we stay, if we don't do anything else. But here's the kind of cool thing about Dalton's law of multiple proportions. If I take the ratio of the brown compound, so I'm going to take the 1.16 grams of chlorine to 1 gram of copper, and I do a ratio of the other one, 0.558 grams of chlorine to 1 gram of copper. Now I get some really interesting information. This ratio, when you divide it all out, is 2 to 1. And what that tells you is that the brown compound of copper and chlorine combined together has twice as much chlorine as the green compound. In fact, just to kind of highlight this more, the formula, the actual formula for the brown compound is CuCl2, two chlorines for every copper. The formula for the green compound is CuCl. So what this law of multiple proportions allows us to do is if we know that two elements are combining to form two different compounds, we can take the ratios of those elements in each compound and figure out how much more one has of the other. And that's what the law of multiple proportions goes through. So we're going to do some practice on both of these laws. So in these two problems we're going to go through, one of the exercises is to figure out which law, if either, is being demonstrated. Okay, so if we look at this first problem, so we have a sample of compound A, a clear and colorless gas, is found to contain 4.27 grams of carbon and 5.69 grams of oxygen. Sample of B, also a clear colorless gas. Now I'm going to stop here. Just because those descriptions are the same does not automatically make A and B the same compound. There's a lot of clear and colorless gases out there that are different from each other. Now, compound B was found to have 5.19 grams of carbon and 13.84 grams of oxygen. So does this data line up with the law of definite proportions, the law of multiple proportions, or neither? In order to figure this out, the first thing we have to do is find the ratio of atoms for both compounds. So compound A, I'm going to take the ratio of oxygen and divide it, or take the amount of oxygen and divide it by the amount of carbon for compound A. Now, the reason I put the big number on top was so that I get a number greater than 1. It just makes ratios, comparing ratios, a whole lot easier if you put the bigger number over the smaller number. Because when I do this, I come out to 1.33 grams of oxygen per 1 gram of carbon. And all I did is just plug that into the calculator and divide. 5.69 divided by 4.27. Now I'm going to do the same thing here for compound B. I'm going to put the, again, bigger number. And the other important thing is if oxygen is on top up here, it should be on top here. Otherwise, my ratios, when I compare ratios, it's not going to be equivalent. Now, in this case, I have 2.6 grams of oxygen to 1 gram of carbon. And again, the way that I got that was I just plugged in 13.84 into the calculator, divide by 5.19. Now, one thing I can tell right away is that this does not conform to the law of definite proportions. How do I know that? Well, one of the qualifications is that those two ratios should be equal. If they were the same compound, and I knew that they were the same compound, those two ratios should be the same. But what this does demonstrate, well, actually, let's finish this first before we see if it follows the law of proportions. Because if it follows the law of definite proportions, I should get a whole number. If I take the ratio of 1, so I'm going to take compound B, and I'm going to divide it by the ratio of compound A. Now again, why did I do B over A? Because B has the bigger number, and that makes ratios a whole lot easier. So if I do all the math, 2.67 divided by 1.33, that ratio comes out to 2 over 1. The law of definite proportion, or I'm sorry, the law of multiple proportions says that I should come out to a small whole number like I did here. And so what does that tell you about substances A and B? Well, A and B are not the same. So A and B are not the same compound. And B has twice as much oxygen than A. All right, and then to round out this lecture, let's take a look at the last problem here. So a sample of compound X, clear colorless combustible liquid with a noticeable odor, is analyzed and found to contain 14.13 grams of carbon and 2.9 grams of hydrogen. A sample of compound Y, a clear colorless combustible liquid, and there's a little caveat thrown in here, then a noticeable odor similar to that of compound X is analyzed to found and found to contain 42.39 grams of carbon and 8.88 grams of hydrogen. So which of these laws is demonstrated if either of them? So we're going to set this up just like we did before. We're going to take a ratio for each compound separately. So compound X, the ratio of carbon is 14.13 grams of carbon. Again, I'm putting the bigger number on top because that makes ratios much easier to view. And so all I do is divide those two numbers, put it in your calculator, and that comes out to 4.77 grams of carbon per 1 gram of hydrogen. Now I'm going to do the exact same thing for compound Y. I'm going to take 42.39 grams of carbon and 8.88 grams of hydrogen. Again, larger number is on top because that makes ratios easier to work with. And when I plug that into the calculator, I find I get a very similar number. Now, since those two ratios are exactly the same, we can say that X and Y might be or are probably the same compound, which um, um, follows the law of definite proportions. But just to be sure, more testing would be needed. So because the ratios are the same, we're going to say that, yeah, this probably is a representation of definite proportions, but we just would need to do more testing to verify that X and Y are actually the same. If they are the same, then that follows the law of definite proportions. All right, that's where we're going to stop with this lecture. When we come back, we will look at what are the things that actually make up an atom. And we'll find that atoms aren't really the smallest things that exist. We'll see that there are much smaller particles that make up an atom.